Today we are going to talk about sections 12.4 and 12.5. Last time we talked about how to look at data. We've looked at standard deviations. We've looked at range, so that's how dispersed the data are. We talked about measures of central tendency, the mean, median, mode, and so on. And today we are going to talk about normalcy. What is it that normal means? We'll talk specifically about the normal curve. Sometimes it's called a Gaussian curve or a bell curve. But notice here on the screen that we have 4 charts. And I have noted, actually in class, in a face-to-face class, I actually asked the students how tall they were, and we created a histogram not unlike this one here on the top left. Now, we didn't have as many students, and so it wasn't quite so smooth even as this one, though this appears rather blocky. And then we extrapolated and said, well, what if we asked everybody in the building? And we said, you know what, I think it would turn out a little bit more like this one on the top right. We'd have more people, and so we would have more individuals in each frequency, or each score, I guess I should say. And it turns out that will regularly happen with a lot of human characteristics, that as we increase our sample size, our curve will smooth out more and more until it's an extremely smooth curve. And that will be our normal curve. That is, once you get a very large population, the size of each class, if you've got a grouped frequency, or the number of scores, in this case heights, that you could include in your histogram would be more. If you've only got 10 people you're looking at, you may have 10 different heights, or you may even have 2 or 3 people that are the same height. But if you're looking at 100,000 people, now you have a whole bunch of people at the same height and a bunch of people at the heights on either side of that. So that's what creates our normal curve. Now, the normal curve itself, we could potentially show like this one on the screen. And they also talk about this 68, 95, 99.7 rule. And that rule comes about because once we graph all of the individuals who meet this particular characteristic, it turns out that 68% of the population is within 1 standard deviation of the mean. Now note that our mean, basically what we usually call average, and our mode and our median are all in the same spot. These numbers across the bottom of the curve are standard deviations. So the mean, median, and mode would be right at the 0. Remember, standard deviation is how far from the mean it is. And so of course it's 0, it's right at the mean. And then we would have 1 standard deviation to the right, plus 2 to the right of that, plus 3 to the right of that. We could turn to the left and subtract 1 standard deviation to get to that next bar, subtract 2 to get to the bar after that, and subtract 3 to get to the bar beyond that. So those are really looking at standard deviations across the board. And so we'll take advantage of that fact. Now notice, as I said earlier, 68% of the population is within +1 or -1 standard deviation from the mean. That middle section is normal. When you hear the word normal, that's what it means. Now think about that. Almost 70% of the population is normal for any given characteristic, which means my teenage daughter and her friends who love to talk about how abnormal they are may not be abnormal. Most of their characteristics would fit within one standard deviation of the mean. So they're normal. In some ways, they're abnormal. In some ways, I'm abnormal. We all have those idiosyncrasies that may put us beyond one standard deviation of the mean. But most people, up to 70% or so, are normal. And the 95% part of this 68, 95, 99.7 rule says that 95% of the population falls between +2 and -2 standard deviations. And 99.7% falls within 3 standard deviations of the mean. We'll look at some examples of that here in a minute, but I also want to take the time to break this down a little bit. If 68% of the population is within ±1 standard deviation, and this is perfectly symmetric about the middle, then that would mean half of the 68, or 34%, is +1, between 0 and +1, and 34% would be between 0 and -1 standard deviation. We could break out these other bars as well. If 95% is between the two, and we've already taken up 68 within the middle, then we could take 95 minus 68 and get 27% left that needs to make up those blue bars. Half would be above, which is 13.5, and half would be below. So now if we add those three blue numbers, we would come up with 95%. Now let's look at the 3 standard deviations above and below. That's 99.7% of the population, but we've already used 95% of the population in the bars that we've already numbered. So we'll subtract 95 from 99.7, and we get 4.7, half of which is on the upper range, and half of which is on the lower range. So 2.35% of the population is between 2 and 3 standard deviations above the mean. Now let's look beyond that. If 99.7 is taken up inside 3 standard deviations above and below, then only 0.3 is beyond that. So 0.15%, half of the 0.3, is above 3 standard deviations, and 0.15% of the population is below -3 standard deviations. So that takes up 100% of the population. So if we were to ask, say, how much of the population is between plus or minus 2 standard deviations from the mean, we could go up 2 and down 2 and come straight up from both of those, and note that that's 95% of the population that fits within that range. So that can really help us figure out how many people out there actually fit within a certain characteristic. Now let's look at a particular characteristic. Say male height in the United States. The mean male height is 70 inches. The standard deviation, let me write these down, the mean is 70 inches. The standard deviation is 4 inches. So we wrote 70 in the middle, since that's where the mean is, and then we added 4 to that to get +1 standard deviation. We added 4 to that to get +2. We're just adding this value of the standard deviation each time. Add 4 to that to get the 82, which is 3 standard deviations above the mean. Now we'll subtract 4 to work our way left, and 70 minus 4 is 66. Subtract 4 again, and that gives us 62. Subtract 4 again, and that gives us 58. It still fits the 66, 95, 99.7 rule. in that 68% of the population is between, now we can just look at the numbers that we wrote down below, +1 standard deviation, -1 standard deviation, and we can tell that almost 70% of the population is between 66 inches and 74 inches. Now that would be 5 feet 6 inches, and 74 inches is 6 feet 2 inches. So most of the population of US men are between 5'6" and 6'2". However, there are some that are shorter and some that are taller, and that's where all of this takes that into account. Now I am about 75 inches tall. So I'm taller than 74, but not as tall as 78, so I don't fall right on that line. If you don't fall exactly on that line, then we need to find out exactly how far away from the mean you are. And that's where z-scores come in. So let's take a look at z-scores. In this example, now brought some text up here, it's actually talking about the mean weight of newborn infants. They say that it's 7 pounds. I believe we calculated z-scores last time, but as a reminder, let me write down the formula. The z-score is found by taking the data item, or the score you're actually looking at. In my height's case, that would be the 75 inches. And we subtract from that the mean, and then we would divide by the standard deviation. That's how we'll calculate a z-score. So looking up here at the problem, we see that the mean is 7 pounds. So that's our mean. The standard deviation is 0.8. The weights of newborn infants are normally distributed, so that fits this curve we're looking at. Find the z-score for a weight of 9 pounds. So I'll often write z with a little 9 down here to remind myself that I'm finding a z-score of 9. So I'll take that data item, which is 9. I'll subtract from it the mean, and I will divide that by the standard deviation. 9 minus 7 is 2, divided by 0.8, and I get a value of 2.5. So a baby who is 9 pounds is up here at 2.5 standard deviations above the mean. Now let's look at a z-score of 6 pounds. 7 is right at the mean, so we actually expect a z-score of 0. Well, let's take that 6, subtract the mean, which is 7, and divide by the standard deviation. 6 minus 7 is -1. Divide that by 0.8. Gives us -1.25. So from the mean, drop 1 1/4, and that would be where an infant who is 6 pounds would sit on the normal curve. Now let's go back to my weight, now that we've looked at that. My weight is 75 pounds, so the z-score, or 75 pounds, would be found by taking that data item, subtracting the mean, dividing by the standard deviation, and I get 5/4, which is 1.25. So my height is 1 1/4 standard deviations above the mean. My height is abnormal. Doesn't mean anything more than I am taller than most of the people out there. And I've noticed that as I walk down the hall, I can often see over people's heads. But that gives us a chance to kind of compare and contrast and see where people lie. Now, I don't know what percentage of people are shorter than I am from this curve. We've got a method to find that, and that'll be in section 12.5, and we're getting to that here pretty soon. There are a few things I need to cover to get to the point where we're ready to look at that, and we'll refer back to this. But let's go ahead and look at a few things more. We've got a problem here that's interesting. We've got a mean of 100. We've got a standard deviation of 16. This is on an IQ test, testing the intelligence quotient of individuals. They ask us, what is the IQ score corresponding to a score of negative 1.5? Well, let's remember the formula. The z-score is the data item minus the mean divided by the standard deviation. So for part A, they give me the z-score. So I'm just going to plug that into my formula. The data item, that's what we're looking for. So I'm going to call that D for data. Subtract from it the mean, which is 100. Divide by the standard deviation, which is 16. Now I need to solve for D. Well, this whole thing on the right-hand side is divided by 16, so I need to reverse that, and I'll multiply it by 16. Anything I do on the right, I need to do on the left. So we'll multiply that by 16. 16 times negative 1.5 is a negative 24. On the right-hand side, the 16s will cancel, and I'm left with D minus 100. Now I've got 100 subtracted. In order to reverse the subtraction, I'd better add, and anything I do to one side, I'd best do to the other. Now I've got negative 100 plus 100, which will equal 0. And I will have the D by itself. Negative 24 plus 100 would be 76. So an IQ score of 76 has a z-score of negative 1.5. I mean, the average intelligence of people out there is 100. So a score of 76 would be 1.5 standard deviations below that. It's about what Forrest Gump had, if I remember correctly, from the movie. Notice in part B, Mensa is a group of people with high IQs. Their members have z-scores of 2.05 or greater. What is the IQ score corresponding to that? Same sort of problem. They gave us the z-score. We're looking for the data item. Subtract 100 from that and divide by the standard deviation. And the process will be identical because I am looking for the variable D, just like I was before. The 16s will cancel on the right, leaving D minus 100. Oops. And then I've got 16 times 2.05, which is 32.8. Just like I did before, I'm isolating the D, so I need to reverse what's happening with the 100. It's subtracted, so I'd better add that. Negative 100 plus 100 is 0. I'm left with just D, and 100 plus 32.8 is 132.8. So if your IQ is above that, you would be eligible to become a member of Mensa. And there are some famous people who are members. An actress named Gina Davis is a member, for example. I think Angelina Jolie's father is as well. Oh, his name just skipped my mind. John Voight. He also, I believe, is a member, but several people are, well, many people, hundreds of people are. You just need to get your IQ tested and then you can join. Used to be they would take the score on the ACT, but they changed that test, so that's no longer an option. Some other ways to look at data, rather than by standard deviation, is by quartile. Like a quarter, they've divided the data into quarters, such that 1/4 of the data are below that line, a fourth between there, a fourth there, and fourth there. 4/4 is 100, so those all meet the whole amount. Sometimes it's nice to break them into quarters. I don't find it incredibly useful most of the time. I prefer percentiles or even z-scores. But sometimes this becomes useful, and there is a problem that mentions the third quartile in our homework. So I want you to know that that's here in this range, because they start on the left, so the first, second, third, and fourth quartile. Now you know where that is, and so when that comes up in the homework, you're prepared to answer that one. Another thing we need to know when looking at data is the margin of error on a report, because we can see data presented to us, but what are the odds that they're absolutely right? Well, they're taking a sample, so there could be some error involved. There's a table in the book that talks about things that people dread, and it says adults dread, and it says that 46% of them dread public speaking. But what would be the margin of error of this particular report? We are given a formula in the book. To find the margin of error, we divide 1 by the square root of the number of people surveyed. And in this problem, that was 1,000. And then we multiply that by 100%. So the square root of 1,000 is 31.62 with a bunch of decimals after it. So I'm going to divide 1 by that. And then I need to multiply that by 100 to get it into a percentile. And when I do, or percentage, I should say, I get 3.16%. So that tells me that their data are right, plus or minus 3.16%. So while they say that 46% dread public speaking, it could be plus 3.16, which is 49.16%, or it could be minus 3.16, which is 42.84%. So the actual number of adults who dread public speaking could be anywhere between those two values, 49.16 or 42.84. Now, their data showed 46%. And it's probably pretty close to that. I mean, 49 and 42 are both pretty close to 46. But you have this disparity that could exist between the results they are saying and the actual results. So when you're looking at data in the news or online, watch for this margin of error. If somebody says, for example, that the temperature in Idaho has gone up by 0.2 degrees Celsius, plus or minus 0.5 degrees, then it's either gone up the 0.2 they report, or plus 0.5, maybe it actually went up 0.7 degrees, or maybe minus 0.5. So it's actually gone down 0.3 degrees. That plus or minus 0.5 tells me that when they say plus 0.2, that is within the margin of error. So it's almost a guess, just as well as any other. It could have gone up and it could have gone down, but they're going to report that value. And they rely on us to understand what that plus or minus margin of error actually means. And the last thing they talk about in this section regarding data and these curves is the fact that not everything actually fits a smooth, normal bell curve. Like this one. There was a report done on female sexuality, and Dr. Kinsey and his associates interviewed lots and lots of women. You can see it was thousands. Over here on the y-axis, they say that's our frequency, and it's well above thousands. It's almost 2,000 in the one column. But notice that the mode is all the way over here at an age of 16 to 20 years old. And that makes sense. If you're talking to women about sexuality, it makes sense that you would talk to a bunch of people in the area where they are most sexually active and not so many people in the areas where they are less sexually active. And so the data are skewed. It is no longer strictly aligned right in the middle and spreads out evenly on either side. And so we need to understand what skewing looks like. And in the book, they talk about two different skew types. It can be skewed to the right or skewed to the left. And they're not talking about where the bump is. They're talking about the long tail on the end. So skewed to the right actually means the tail goes to the right. And in the normal curve, where mode, mean, and median were all in the same spot, what happens is the mean and median get pulled to the right when you have a tail to the right. When you have a tail to the left, the mean and median get pulled to the left. And that's why they call that skewed left. And the first one was skewed right. So this data set that Dr. Kinsey included was skewed to the right. So the mode, which we can clearly see, the tallest column, is here at the 16 to 20, but we expect the mean and the median to be pulled a little bit more to the right. And that fits with what we've experienced as we've looked at frequency curves and histograms. But we do need to understand that not everything really does fit a normal curve, and sometimes we have a skewed curve. All right, let's jump into section 12.5 now. I told you we were going to look at my height from a different perspective. What percent of the population is shorter than I? And this is the type of table that will help us. In 12.5, we're going to use a number of tables like this. And if you need one, it will be provided for you in the problem. So you won't have to memorize this. You won't have to have it printed out next to you, but you do need to know how to read it. When I was a kid, I would take standardized testing and the results would come back and it would have my score and a percentile. That percentile told us what percent of the population scored lower than I did on that particular section of the exam. And so that's what percentile means, but we can use that when we are looking at information, specifically things like my height. Percentile is the percent scoring lower or less than our data item. So with height, it would be the individuals who are shorter than. In weight, it would be the people who weigh less than. In how long a pregnancy lasts, the people who had a pregnancy that lasted shorter period, and so on. So remember, my z-score was a 1.25. So let's come up here and we'll look at the 1.2. And it tells me that 88.49% of the population is lower than 1.2 standard deviations above the mean. Now, I was 1.25, so I'm a little above that, somewhere between 88.5 and 90.5, so maybe 89% of the population, 89.5%, are shorter than I am. Doesn't mean better, doesn't mean worse, it just means that's the way it works. They are shorter than I. And so we will use this. We'll find a z-score for a data item. We'll go to the table and we will figure out what percent of the population scored lower on that characteristic than the data item we're looking at. That's how we use these tables. Let's look at a problem and see how that works. And I know I've got the table in the background, but I think that we'll still be able to see it well. I'm going to go ahead and put a little drop shadow on this so the problem sticks up a little better. Oh, I'm on the wrong. I needed it here. It'll just show a little better above the table if I have that drop shadow. All right. So the problem says, according to the Department of Health and Education, cholesterol levels are normally distributed. For men in that age group, the mean is 178.1. The standard deviation is 40.7. What percentage of men have a cholesterol level less than 239.15? So let's find the z-score. Oh, that looks funny with the drop shadow. So let me write on a different, oh, now I've lost my drop shadow. For some reason, I feel I really want that, but I will write on a different layer. So the z-score of 239.15, we will calculate by taking that 239.15, subtracting from it the mean, and we're told that's 178.1. We'll divide by the standard deviation, which is 40.7. I plug that into my calculator, and I find it really easy to use the fraction portion of my calculator to make sure that PEMDAS is followed the way I want it to be, and I'm not making any mistakes when I type it in. You may want to use parentheses. That works just as well to force it to do what we need done. And the z-score is a 1.5. So we go to our table, and 1.5 is in the 93.32 percentile, which means 93.32% of the population has a cholesterol level less than 239.1. Now let's look at another problem. Probably put a drop shadow on that. I probably shouldn't, but there we have it. All right. So we get a new layer here. And lengths of pregnancies, again, normally distributed with a mean of 266, standard deviation of 16. What is the z-score of 274? So we'll take the data item, 274, subtract from it the mean, which is 266, and divide by standard deviation, which is 16. Back to my calculator. 274 minus 266, all divided by 16, and I get a value of 0.5. So a z-score of 0.5 is in the 69.15 percentile, which means 69.15% of the population has a pregnancy shorter than 274 days. That's exactly how those are going to work each and every time. Well, let's look at another. How about this one? Now, this is a little different. We're going to have to think about this one for a minute, I think. It's okay. We know how to think. All right. We've got self-employed Americans working each week, normally distributed. They give us the mean of 44.6 hours. The standard deviation is 14.4. What percentage of the self-employed individuals work between set 37.4 and 80.6? Let's find the z-scores of each of those. First one, 37.4. Subtract the mean of 44.6. Divide by 14.4. Back to my calculator, 37.4 minus 44.6 divided by 14.4 gives me negative 0.5. Which is right there. The negative z-score just means it's to the left of the mean. The z-score for 80.6 could be found by taking 80.6, subtracting 44.6, divide by the standard deviation, and that gives me a z-score 80.6 minus 44.6 divided by 14.4 is 2.5. So a z-score of 2.5. That's right here. Now, what percent of the population is between those two? These percentiles are just less than. So let me see here. I'm going to first erase all of this as it's kind of in my way. Well, maybe not all of it, but close. Okay. Come back up. So normal curve, not a great one, but that's okay. Got a mean. So we're at negative 0.5. So somewhere in here is the 37.4, and it's got a percentile. And then we've got plus 2.5 is over here, and it's got a percentile. How can I find the area in between the two? Well, it looks to me, if I take this big one and subtract the little one, I'll end up with the in between. So let's take the 99.38 and subtract from it 30.85, and that is exactly how we approach this problem. So 99.38 minus 30.85 is 68.53. So 68.53% of the self-employed Americans work between those 2 hours. So that's a little twist from what we've done before, but that's taking advantage of the fact that these are all less than values, all of the percentiles. As a matter of fact, we're given a table in the book that helps highlight that. If we see this table here, it can help really show what we've got. If you need percentage of data items less than a given data item, just use the table and you're good. If you need a percent that is greater, find the z-score for the table and subtract the table number. Oh, I should have gone down just a little more. Subtract the table number from 100. So if we were in the 70.5 percentile, that means 70.5% are below. If we need above, we just look at the other side. If 70.5 are below, then 100 minus 70.5 are above. So just subtract the number you have from 100, and that gives you above. If you're looking between two data items, subtract the percentile of the one from the percentile for the other, just like we just did. And that will let you use those tables to find percentage below, percentage above, or percentage between two values using z-scores. So find the z-score, which is how many standard deviations the data item is away from the mean. Go to the table to get the percentile, and then either use that number to find the below, subtract that number from 100 to find the percent above, or take two z-scores and subtract the numbers you get from the table. And those will give you the values you need. I hope that's helped. If you have questions, of course, just like always, let me know.